I'm hoping so that today I'll complete introduction. I don't expect it to spill over beyond 2 hours. So I'm saying 1.5 to 2 hours, not more than that. Okay? Then we'll have to look at power devices. What are all the different power devices? How are they having, a specific characteristic? Why they are having that kind of a characteristic? To some extent, we'll look into the physics. I am definitely not a device physics person, so I will not be able to really deal with that in great detail, but we will try to look at basically how the structure of the devices, why the ratings are limited, why maybe on-state losses are high or low and such things. So we'll look at devices, their characteristics and so on. I think it should take anywhere between 4 to 5 hours because I am not really going to deal with it in great detail. Okay? So I should be able to finish it within this. After this, we'll start off with rectifiers. So in rectifiers, we'll have to look at half wave, full wave, uncontrolled, fully controlled, semi-controlled. That is, we can use thyristor, we can use diode, a combination of thyristor and diode, R load, RL load, RC load, RLE load. All those things we have to look at. So it is going to take a while. I expect that it should be between 8 to 10 hours. After this, I would like to deal with AC to AC converters. So we will look at AC voltage controller and cycloconverters, both. But these are not dealt with in many of the books because they have specialized applications. So I am also thinking that I will not concentrate on this to a very large extent. So hopefully it should be over in 3 to 4 hours. I don't want to really dwell on this for too long. Okay? Then comes DC to DC converters. So in DC to DC converters, I just showed you 20 volts can be reduced to 10 volts. But we also have the opportunity of increasing from 10 volts to 20 volts, which is known as boost converter. What I showed you just now was a buck converter. So we might look at boost converter, which is a step up, buck converter, which is a step down converter. We'll look at a converter which can do boost or buck, which is step up or step down converter. So these are the basic configurations of converter we'll look at. If time permits, I would like to go for a few more converters which are used extensively in power supplies. Power supplies generally require isolation, because of which there will be a transformer in between. So when you insert a transformer, the behavior of the converters becomes somewhat different. So we will have two configurations. Whichever has isolation, we call them as isolated DC-DC converters. Whichever do not have transformer, which will not be isolated from the input to output, we call them as non-isolated. So I would like to touch upon isolated converter as well, although we will concentrate more on non-isolated converters. So I expect that if I include isolated converter, I will require at least 8 hours. Maybe I would say 7 to 8 hours will require for DC to DC converter. Okay? Then comes DC to AC inverter. DC to AC inverters, mainly we will be talking about, I have a DC voltage, and I want an AC voltage. Maybe single phase, maybe three phase, maybe I have R load only, maybe I have RL load. Or I may have an RLE load, like a motor, because that also has a back EMF. So we'll be looking at all those configurations in single phase and three phase. So this will require more duration for us to deal with. So let us say 9 to 10 hours if I am talking about voltage to voltage, DC voltage to AC voltage conversion. If I am talking about DC current to AC current conversion, it is a different ball game altogether. So let me see, if I have time, I'll deal with the current source inverters. If I don't have time, I will ignore current source inverters for now. But let me see how the time goes. How many hours are over according to this? Higher number, le lo. 2 plus 5, 7, 17, 17, 21, 21 plus 8, 29, 39. So I have 3 more hours. I think I'll require those 3 more hours for applications. Because I think if I don't tell you the applications, it doesn't make much sense. So I'll have to have some applications. In fact, there is more to power electronics than this, but I'm only uncovering some portions so that you would be able to proceed further if you are seriously interested in a particular topic. So I would say applications may be 3 to 4 hours. And this includes problem solving as well. That's what I am a little worried, how we are going to deal with it. Let's see. Okay? Yes? Any specific questions? Yeah? Evaluation policy. Before that, let me give you the reference books. Don't tell me you are not going to read any books. You better. So as far as reference books go, all the books are titled Power Electronics, so I don't have to write anything else. Most of them will say Power Electronics, Devices, Circuits and Applications. So the title is fundamentally Power Electronics. It may be Devices, Circuits and Applications will be the smaller subtitle. Okay? There is one book by M.H. Rashid. This is from Pearson. This book, at least older edition, had some mistakes. So I would like you guys to study this with a little bit of caution. I know where the mistakes are, I'll tell you. As I go along, I'll tell you if there is a mistake in this book in a particular chapter. But the latest edition I have not looked at. I have to look at that as well. Older edition had some mistakes in rectifier as well as AC voltage controller. So let me take a look at this and then tell you. So this is one of the reference books which is easily available, not a problem. The second one is N. Mohan et al. There are two more authors. Okay, this is from John Wiley. This book does not have any mistakes, but this is like a typical foreign author book which does not have many problems to work out. You might have 1 or 2 examples that are done, and it's a little of higher level. Sometimes it is a put off for a beginner, like Fitzgerald in machines. Okay, Fitzgerald is very well written, but it is a little higher level for a beginner. So Rashid is a little lower level, whereas Ned Mohan is a little higher level. So this is from John Wiley. Another book which is pretty good is by Daniel W. Hart, H-A-R-T. This used to be from Tata McGraw-Hill. Now I think Tata has dissociated themselves from McGraw-Hill. So it is McGraw-Hill India, that's what it is. So This book is written in a very, very simple manner, and he has done a pretty good job of all the circuits, but he has done an especially good job in DC to DC converters. He has done a very, very good job in DC to DC converters. Right? So this book is pretty good. And this is from McGraw-Hill, India, so it is not very expensive. It's like 300, 400 rupees, something like that. Okay? There is one more book, Issa Batarshe. I don't know how you pronounce this. Okay? Maybe a South American author. This book is very, very good for DC to DC converters. He has also given others, but DC to DC converters is dealt with very, very well. In fact, anybody who works on SMPS and all, I generally ask them to study this book first to understand DC to DC converters thoroughly. This is from John Wiley. And of course, you might have heard of this book. There is one by Erickson. Erickson is also from Pearson. This is also from Pearson Education. There are further several books available, but if you actually primarily refer to this book, that is good enough. But if there is something I am dealing with from some other book, I'll let you know. Right? Fine? So these are the reference books. Okay, so we are going to start on devices. So we will have three different kind of devices that we will have to discuss in this particular course. So uncontrolled devices, then semi-controlled devices, and fully controlled devices. These are the three types of devices that we are going to discuss. As far as uncontrolled device is concerned, as I told you, the major device that we are going to discuss is diode. And we always add a power as a prefix. So it will be a power diode that we will be discussing briefly, because you guys know about diodes. There is hardly any difference between the two. So we'll only highlight the differences. And if at all in the operating condition, if it is somewhat different, I'll also highlight that. Okay? And semi-controlled device, we are going to normally talk about SCR, silicon controlled rectifier. Many of the books use thyristor and silicon controlled rectifier synonymously. But thyristor actually indicates a family of devices. Some of them may be in fully controlled configuration, some of them may be in semi-controlled configuration. So I would rather say thyristor refers to normally a family of devices, some of them being semi-controlled and some of them being fully controlled. So in fully controlled, as far as the thyristor family is concerned, we have something called GTO, gate turn off thyristor. Then there is one more called IGCT, that is integrated gate commutated thyristor. Okay? These two belong to thyristor family, yet it can be controlled during turn on as well as turn off. There is one more called MCT, which has not become very popular. So it is almost, extinct. Mass controlled thyristor. So metal oxide semiconductor controlled thyristor. So mass controlled thyristor is MCT. So these are the three types of thyristor devices. which are coming under the category of fully controlled devices. But yet, some of the people talk about thyristor synonymously with SCR. SCR is particularly a semi-controlled device. Only on condition can be controlled. Off, it is very difficult to control. You can't turn it off very easily from the gate terminal. That's what I mean. Otherwise, you have to take, a roundabout approach to turn it off. That is one of the problems with thyristor, especially if I use it in a DC circuit. Because in a DC circuit, I will normally connect it in forward biased condition. How will I reverse bias it? Unless I apply a negative voltage. In AC, automatically the voltage will become negative after some time. But in DC, it's not going to happen. So generally, thyristor family of devices, especially SCR, it poses a big difficulty when I use it in DC circuit. Right? Apart from that, we also have power MOSFET. I am just adding power to everything. MOSFET is a normal transistor, metal oxide semiconductor field effect transistor, but power MOSFET is used in power electronics. Similarly, BJT, I should have added power, but I am just not adding right now. I think you guys can add it, not a problem. Power BJT, power transistor, that is bipolar junction transistor. And we also have another device which is exclusive to power electronics, which is hardly ever used in electronics, which is known as IGBT. IGBT is actually a hybrid of transistor and MOSFET. Both of them hybridized together. A new device was developed by one of the Indian scientists who is sitting still in NCSU, North Carolina State University. So this was developed by him, IGBT, and it has become really, really popular. And this is exclusively used for medium power ratings, hundreds of kilowatts rating. So this is known as insulated gate bipolar transistor. So this is actually, as the name indicates, the gate will be insulated from rest of the device. So it's known as insulated gate bipolar transistor. So these are the devices we will be discussing. In fact, MCT, I will not dwell much. IGCT, very limited details are available. It is an exclusive property of ABB. ABB is using IGCT extensively. So we don't have much of information about IGCT. But rest of the devices, at least I'll cover the characteristics, their brief construction, and how to select a particular device for an application, how to protect the device, and what are other operating conditions we will be encountering. This is what we would be doing in this particular session. So let us start off with diodes. Normally, in any ideal switch, what we would expect is, during on condition, it should have zero voltage drop. And during off condition, it should have zero leakage current. But definitely real devices are far from being ideal. That's why we call them as real devices. So apart from the aims or goals that I enlisted yesterday or in the last class, saying that we would like to increase the power capability to infinity, we would like the voltage capability to infinity, current capability to infinity, we would like to have the frequency to reach infinite value so that you will be able to operate it very fast. And apart from that, we should also look at on-state resistance has to be minimized to zero. If I want a device to be ideal, I have to make the on-state resistance to reduce to zero. Similarly, R off should be infinity, which means I should have forward voltage drop to be zero, and similarly I leakage during the reverse to be zero. So these are the characteristics that I would expect of an ideal device. Right? So also is the case with, if I want the diode to be ideal, I should definitely have these properties. So if I try to draw the ideal characteristics of a diode, I should show it as though the current will increase, vertically. I am talking about, this as the voltage and this as the voltage and this as the current. What am I talking about? Yeah. So I am going to have voltage to be 0. So this is voltage and this is current. So I am going to have essentially, in the other condition, the current is going to be 0, the reverse bias condition. So this is the forward voltage. So this is the positive voltage. Obviously voltage is increasing in this direction and current is increasing in this direction. So this should have been my ideal characteristics. But as you guys know already, what we saw in ELL 100, even subsequently digital electronics course you might have seen. So we would normally see that the current starts increasing after a little bit of forward voltage drop, and it increases, steeply. The current increases steeply like this. And of course, on the other side, the voltage, actually the current will be 0 for a long time. But if you increase the voltage beyond a particular value where the device would break down, I'm going to have a steep increase in the current. And that is a destructive breakdown. Most of the times it will be a destructive breakdown. So this is the reverse voltage. So this is the voltage and this is the current. And I'm going to have the real characteristics somewhat like this for the diode. Normally for the electronic diode, what we use at low power level, we will see for a silicon diode, V forward will be about 0.7 volts. But in this particular case, when we are using it for higher ratings, we might increase the length, and construction wise what is done normally is there will be a N- substrate with a very light doping, and on that we will make P plus and N plus. So excess amount of doping is done on a N- substrate. So normally what is going to happen is that you will see that the resistance is somewhat larger, because of which, on state resistance I am talking about. So the forward voltage drop will also increase. And if between anode and cathode, if I am going to apply a large voltage, because it is a large power rated device, in all probability the length of the device also has to increase somewhat. So if you look at the normal diode that you use in electronics lab, it will be really, really small. But if we look at power diodes which are rated, single-handedly they can handle 25 to 30 megawatts. Some of them can handle 25 to 30 megawatts single-handedly. So I may have 6 to 7 kilovolts as the voltage rating and 4 to 5 kiloamperes as the current rating. So if this is the rating of the device, the maximum current and maximum voltage that can be borne by the device, then obviously it is going to handle anywhere between 24 to about 30 or 35 megawatts. So which means it has to be definitely longer. So the voltage drop can go as high as 2 to 3 volts. When it is actually in on condition, you can see that the voltage drop can go as high as 2 to 3 volts. But 2 to 3 volts out of 6 kilovolts or 7 kilovolts is minuscule. So that's all right. Whereas when you work with 15 volt circuit, 0.7 volts itself is a big deal. So you definitely would not like to increase the voltage drop any further. Then it is far from being ideal. So these diodes can handle, can have a voltage drop of almost 2 to 3 volts most of the times. Now, as far as this diode is concerned, because it can single-handedly handle such a large value of current, it also takes a little while before it turns off. So generally, if you look at the turn-off characteristics of a diode when you are reverse biasing, maybe the current was originally like this. The current would come down rapidly. It will go very briefly into the reverse condition, very, very briefly, and then it will come down to zero current or leakage current. This is the way normally the diodes depict the characteristics as far as the current is concerned. So this particular duration from where the current is becoming 0 to the current is becoming negative and then coming back to 0. This is known as reverse recovery time, TRR, reverse recovery time. So the reverse recovery time essentially depends upon how quickly the recombination takes place and all the charge carriers are swept out, and then ultimately nothing is present there. The depletion layer is again built up. So that takes up a little more time, especially in the case of a power diode, because the number of charge carriers will be enormously high, because we are going to have definitely a huge amount of current being carried. So all of them recombining will take at least a few microseconds sometimes. So reverse recovery time reduction is one of the key features as far as the research in diode is concerned. They want to improve that as much as possible so that you would be able to operate it in high frequency of operation. If it can be operated in high frequency, that means it has to recover very fast. That's what it means. So reverse recovery time has to be brought down if I want to operate it in high frequency circuits. Now there are mainly three types of diodes we encounter in many of the power electronic circuits. One is converter or power frequency diodes. Power frequency is obviously 50 Hertz. So we use it for rectification in most of the cases with the 50 Hertz supply. So in those cases, we call them as power frequency diode. And that's 20 millisecond cycle. So 10 millisecond correspond to positive half cycle, another 10 millisecond corresponds to negative half cycle. So I have sufficient time for the recovery. I don't have to worry about improving the reverse recovery. So power frequency diodes are available at extremely large ratings. Like what I told you about 30 megawatt or 25 megawatt, they are all power frequency diodes, and they act pretty slowly compared to rest of the devices that we see in power electronics. So these are less costly, very robust, available at high power ratings. So we would be able to use them for high power, low frequency applications. So these are generally high power and low frequency applications. So they are pretty slow and they can handle very, very high power. And the major application is normally rectifier. That is the major application. The second type of diode we normally see again in the market is fast recovery diode. Fast recovery diode, as the name indicates, it has to recover from the conducting condition to the non-conducting condition very quickly as it can. And these are used generally in two types of applications. One is freewheeling. I will explain both these right now. And the other one is feedback diode. Let me explain what is a feedback diode and what is a freewheeling diode, because we will revisit this when we go to chopper and when we go to the inverter. So I would like you guys to remember what we are discussing now. Okay? So let us say I am using a chopper circuit. I have a DC supply here. You guys had done a project in ELL 100. I am revisiting that, basically controlling the speed of a DC motor. So I have a motor here and I am going to apply the voltage, intermittently with the switch. The switch is not a mechanical switch, it is a semiconductor switch. I am not going into the details of the semiconductor switch. It is an on-off control switch, obviously. So I should be able to turn it off also. It cannot be a diode. That's what I mean. So I am going to have, whenever the switch is on, so if we are turning the switch on, At that time, I'm going to have a current flowing like this, right? This is going to be the current. But as you all know, motors have some inductance. So if I try to open the device, then I'm going to have a huge amount of L di by dt because the current will be forced to go to 0 instantaneously, which is definitely not good for the switch as well. Because if I am having an inductance here, that means I'm going to have initially I is not equal to 0 when the switch is on, right? When I'm going to turn the switch off, I will be equal to 0, right? And if the switch is off and I become 0, you know, abruptly the current goes from a finite value to 0 in no time. So I am going to have a huge amount of L di by dt. So L di by dt will be very large if I try to simply open the switch without having any alternate path for the current. So to give an alternate path for the current, I would like to put a diode here. This is the diode that I am going to put right across the motor drive. And I call that as a freewheeling diode. Freewheeling diode is that diode which will carry the current which is stored, which is because of the energy stored across the inductance. So it is like a flywheel. It is essentially trying to, you know, de-energize the inductance by circulating the current through itself and whatever is the load. So now during freewheeling condition, if I try to look at the current will go like this through the diode. The current is still flowing in the same direction. Please note that. The current direction cannot change in an inductance. It has to remain in the same direction. And now the switch is open. When the switch is open, the freewheeling diode, let me call this as DFW. Freewheeling is FW. So I'm just writing DFW. So the freewheeling diode carries the current when I am switching off this particular semiconductor switch. And now the conduction path is essentially through the diode. So it is as good as short circuiting the motor drive. I have short circuited the motor drive with the help of a diode. But the energy stored in the inductance is finite. So obviously the current cannot go to infinity. Current has to slowly decrease because inductance stored energy. Previously di by dt would have been positive. Now di by dt would have been negative because there is no other source that is available for the motor drive. The back EMF will also be opposing. I hope you understand. If I try to look at the back EMF will be plus here and minus here. That is how EB will be, which is opposing the current, obviously. So I will have the diode taking over the current and I call this as freewheeling diode, and this is going to happen repeatedly every time I turn on and turn off the switch. Which means this diode has to work as fast as the rate at which the switch is working. So obviously it cannot be doing it slowly. So that is why this is known as a fast recovery diode. It has to recover fast and it has to go along with the switch. Whenever the switch is not conducting, this will conduct and vice versa. That's how it will be. There is one more application which I told you as feedback diode. For this we should know roughly what is an inverter. So let us say I have a single phase, DC to single phase conversion circuit. Okay. So these are the four switches. This is plus and this is minus. Okay. And I am going to have a load connected here. Here is where my load is. The load is here. So let me call this point as A and this point as B. Let me call this as 1, this is 1 dash, this is 2 and this is 2 dash. Whenever I am having 1 and 1 dash conducting, the current would go in the load in this particular direction. This is for 1 and 1 dash. Whereas if I have 2 and 2 dash conducting, I am going to have the current going in the opposite direction. You get my point? So, I would have alternating current flowing through the load depending upon, whether I am keeping 1 and 1 dash on for some time and 2 and 2 dash for some time, and how frequently I am doing the switching action. That will decide the frequency of this alternating current that is flowing through the load. So, I can adjust the frequency very, very well by adjusting the rate at which I am operating these devices 1, 1 dash and 2, 2 dash. And so this becomes an inverter. From DC I am converting this into AC. Please note again that these switches have to be turned off forcefully because it is connected to DC. So if I actually have a thyristor, for example SCR, it is going to continue to conduct. Right? Because I told you that as far as thyristor is concerned or SCR is concerned, turn on is in our hands, but turn off is not in our hands. Right? So normally we use probably IGBT or IGCT or MOSFET or BJT, one of them for this device. Now let us say this load is RL load, R and L in series. Okay? Now if I am having 1 and 1 dash on, I am going to have a current going like this, go through like this, through this green, and then it is going to come through like this. This is going to be the current path when 1 and 1 dash are on. Now I want to start the negative half cycle, right? So if I try to draw the voltage, I am probably going to have VAB when 1 and 1 dash are on, I am going to have positive voltage, right? And if I try to draw the current, maybe the current would have been increasing like this. RL transient, right? So obviously the current will increase. It would not have reached steady state yet in all probability. Now I want to turn on 2 and 2 dash. Before that I would like to turn off 1 and 1 dash. When I turn off 1 and 1 dash, the current is still not zero and I have an inductance sitting in the load. So obviously I can't make inductive current abruptly zero. If I do that, I will get a very large voltage. So I should provide an alternate path. So for providing an alternate path, the current is still flowing in this direction. I can put one diode here and one more diode here. Right? The current is flowing in this direction. So if I may call this as D2 and D2 dash, I will have the current flowing through D2 and D2 dash back to the supply. So the supply is actually getting the current like this. So it is flowing into positive terminal and flowing out of negative terminal through D2 dash. That means the stored energy in the inductance is charging the battery. If I say it is a battery, the battery will get charged from the stored energy in the inductance. That is what is going to happen. So it is feeding back the energy that is actually already there in the inductance. So this is generally known as the feedback diode. So feedback diodes are an essential feature of an inverter whenever I have RL load. If I don't have RL load, if it is only resistive load, which is a very, very rare thing in the actual electrical circuits, I am not going to be using a feedback diode. But if there is inductance, I definitely need to use a feedback diode. If I don't use a feedback diode, my devices will conk out right away because L di by dt will result in a very, very high voltage. Right? So the devices will conk out because they are designed only for a particular value of voltage. So fast recovery diodes are used in choppers generally as freewheeling diode. Even in rectifier it may be used as a freewheeling diode, but in all probability it need not be fast recovery if it is a 50 Hertz rectifier. But in inverters and in choppers, normally we operate them in kilohertz or tens of kilohertz. So they have to be fast recovery diodes. The third type of diode is Schottky diode. Schottky diode is basically, rather than doping the semiconductor with P and N, it may be a simple semiconductor material of N which is having a junction with metal. So you will have a metal and semiconductor junction, one of them acting like an anode, the other one acting like a cathode, and that will function like a diode. So in Schottky diode, because there is a metal and semiconductor junction, I am going to have the resistance of this material will be generally much smaller compared to a normal semiconductor diode. So the forward voltage drop will be as low as 0.1 or 0.2 volts. So V forward will be very low. But on the other hand, the leakage current can be higher somewhat. The leakage current could be somewhat higher because the resistance as such has come down somewhat. So because of which forward voltage drop coming down, but simultaneously I am going to have the leakage current slightly increasing, right? And these generally are designed only for lower wattage rating. Generally these are not available beyond 300 volts or so, and maybe a few tens of amperes, 10 or 20 amperes, that's it, nothing more than that. So the rating that is available in Schottky diode generally is very small because of the limitations that we have in the form of leakage current. Leakage current will otherwise increase tremendously if I go for higher and higher voltages. So generally they are designed only for lower power ratings. These are mainly used in power supply applications. Again, power supply applications, because if you look at many of the regulated power supplies that we have in the lab, which are definitely not SMPS, they are not SMPS normally, they are regular linear regulated power supplies. Those will be 15 volts or 5 volts or 3.3 volts and so on. Out of that, instead of dropping 0.5 volts, if you drop only 0.2 or 0.1 volts, it's better. You have a better regulating capability. So you would like to reduce the drop as much as possible in power supply applications. So because of which normally Schottky diodes are used in power supply applications. Okay? And similarly in power supply applications, again, if you look at the rectifier that we use in power supply normally, you would see that if this is my output side of the rectifier, invariably I will use one Schottky diode here, one more Schottky diode here. I would connect them together, and from the center tap I would connect it to the load. This kind of rectifier we call as center tapped rectifier. I don't know whether you have come across this. So this is a center tapped rectifier. Center tapped rectifier will have generally a transformer always associated with the rectifier circuit, and you will have only one diode conducting at a time. At a time you will not have more than one diode conducting. So which means this is going to have only 0.1 or 0.2 volts drop if I am talking about a Schottky diode. Whereas you guys must have definitely learnt about bridge rectifiers as well. So if I look at a bridge rectifier is somewhat like this, right? And here is the load. And I'm going to have the power supply connected here. This is the power supply connected. I don't need a transformer, that is a major advantage, no doubt. But I will always have, say, D1 and D1 dash conducting, or D2 and D2 dash conducting. Two diodes will conduct at a time. Without two diodes, काम नहीं चलेगा. So I will have the voltage drop corresponding to two diodes in this case, whereas in a center tap rectifier, I will have the voltage drop only corresponding to one diode. So generally, center tap rectifiers are preferred in power supply applications because I have to only manage one diode drop. Whereas in the other case, 2 diode drops, which will amount to maybe, especially if it's a silicon diode, 1.5 volts, 1.4 volts. I may get a very large drop out of 5 volts power supply, which is definitely not a good thing. That's the reason why generally bridge rectifiers are more used with motor drives or large power applications, whereas center tap rectifiers are generally used with power supply applications. And power supply applications want to minimize the drop, so Schottky diode also go hand in hand with this. Right? So much so for the 3 types of diodes. Now, as far as the diode protection is concerned, how do I protect the diode against over voltages, over currents, high di by dt, high dv by dt? Right? Normally we use semiconductor fuses in series with the diode. Semiconductor fuse should have an I square T rating, I square R multiplied by dt integral. That is what is the overall heat generated, right? I square R is the power loss, which is also manifested in the form of heat. So, I square R dt integral. This is what gives me the overall heat generated. So, I square T rating corresponds to how much is the heat a particular device can withstand. Okay, in the form of energy. We talk about this in the form of energy. So, I square T rating of a fuse has to be smaller than the I square T rating of the device, so that the fuse conks out first before the device is affected. Otherwise, it doesn't make sense. The device will go bonkers, right? We don't want that to happen. That's the reason why we have to use a fuse rating whose I square T rating is smaller as compared to the device rating itself. So, device will not conk out. Before that, the fuse will burst. That's what will happen, right? So, semiconductor fuses are normally used for overcurrent protection. So, if a large current flows more than the rated current of the device, in all probability the fuse will first go off, because of which the device will be protected. Right? No other hi-fi protection is normally used for the diodes. And as far as the over voltage is concerned, sometimes we may use a Zener, but most of the time forward condition it will not have much voltage, so you don't have to worry about it. In the reverse condition we might have to use a Zener. Sometimes we might use a Zener. That's what we will do. But generally over voltage protection of diodes is not talked about much, because hardly ever we subject it to a higher rating than what it is required to withstand normally. But di by dt protection we have to give normally for the diode, and di by dt protection is normally given by having a small inductance in series with the diode. If I have a small inductance, it will automatically reduce the rate at which the current is rising. For example, we actually looked at the chopper, right? Here if you look at it, maybe the DC motor drive was carrying hundreds of amperes of current. When the diode is taking over, it has to abruptly take that 100 ampere, which is definitely not good, because di by dt in that case will be enormously high. So the semiconductor material can break down. So if I put a small inductance here in series with the diode, very small inductance. Very often what happens is, if I have a thick conductor connecting the diode to the DC motor drive, that itself will have an inherent inductance which is good enough most of the times. But we'll have to make a calculation before we decide whether that inductance is good enough or whether I have to add some external inductance so that the current di by dt is limited within whatever is the tolerable limits of the device. So di by dt protection as a rule is always implemented for all devices by having an inductance. Whereas dV by dt protection, this is done with the help of something called an RC snubber. We use something called an RC snubber for making sure that the dV by dt protection is implemented. So let us say I have a diode and I have a load. Right? And I'm going to have probably, the lead inductance, it is not going to be very, very small. Maybe it is some value which can still affect the diode because probably the current is very high. L can be small, but di by dt could be very large, because of which I may have a large voltage coming across the diode if I don't give adequate protection. So let us say for some reason this diode will stop conducting and something else takes over. Right? Or the current is trying to come down to very, very minimal value, whatever, through the diode. I'm talking about the diode. So maybe there is some other alternate path. If I'm going to make the current through the diode abruptly zero, then whatever is the lead inductance L multiplied by the di by dt will be a very large value of voltage. It will be coming across my device. So the device can break down. So if rather I give a R and C right across this device, right? In which case, at least there will be an alternate path provided for the current for a pretty short while. So I will have basically, if the current had been flowing earlier like this, now it will try to probably flow through this and to the load. So now the capacitance will slowly get charged because the current, load current is now deciding at what rate the capacitance is charging. So the RC time constant will decide the rate at which I'm going to have the increase in the voltage of the capacitor. So the voltage across the diode will also be somewhat limited by the RC time constant of the circuit. So this RC circuit is generally known as snubber, which will allow a gradual rate of rise of voltage across the device, which will definitely not allow the device to break down because of high dV by dt. So the snubber is commonly used in many of the semiconductor circuits to protect them against high dV by dt. Similarly, inductance is used in many of the semiconductor devices to reduce di by dt value. So these are common features in many of the semiconductor circuits. Before we conclude the topic of diodes, very often I might have to use multiple diodes in parallel or multiple diodes in series if I want to have a higher and higher voltage circuit. For example, I told you that one particular diode can withstand 6 kilovolt. Let's say I have a 30 kilovolt circuit which I want to operate with the help of a diode. Then I might have to put at least 5 of them in series. Right? In fact, 5 would not be sufficient because I also have to include a factor of safety. In case there is a spike or in case it is an AC, RMS value may be 6, but the peak value will be 6 times root 2. So I have to definitely put a factor of safety and then choose maybe 7 or 8 or 9 devices. So if I want to increase the rating, I have to include many devices in parallel or series. So I may have maybe one diode and another diode, for example, in series, to withstand a total voltage of VT, V total. Right? If it is conducting, I don't have to worry much, because while conducting it is going to have a drop of a few volts. So there will not be very large voltage coming across the devices. But when it is not conducting, if I'm going to have plus here and minus here, when it is not conducting, I'm going to have the entire voltage borne by these two devices together.